So dear learners, today we are going to see the resolution of forces. Resolution of forces into its components. We have already seen that if there are two forces acting on a body simultaneously, say like this, say P1 and P2 at an angle of theta degree, then we can find the resultant of these two. That is, we can replace these two forces by single force using a parallelogram. We will construct a parallelogram in such a way that these forces P1 and P2 will be represented by the adjacent sides of a parallelogram like this. So this is P2 and this is P1, and we will construct a parallelogram like this with P2 as this side and P1 as this side. Okay, so these are parallel and these are parallel. Okay, so we will construct this parallelogram, and we know the diagonal of this parallelogram which is passing through the intersection of P1 and P2. This will be the resultant. Okay, or in other words, this can be represented as a single force R. Single force R at an angle alpha with the horizontal or with the P1, we can say, and the equation for magnitude of this resultant is R equal to square root of P square plus Q square plus 2PQ cos theta. Clear? And the angle alpha, that is, as this is a vector quantity, we need to specify the direction also. So the direction of this resultant R is specified by the angle alpha with the force P1 or with the horizontal. So alpha can be written as tan inverse Q sin theta divided by P plus Q cos theta. This is the equation for alpha. Okay, so these are the two equations we need to remember to find the resultant of two concurrent non-parallel forces. Two concurrent non-parallel forces. Okay, so this is using parallelogram law of vectors. So here we have replaced or merged two forces into a single force. Okay, combine these two, the effect of these two forces into the effect of a single force. Okay, so if there are a number of forces are acting, instead of these two, if there are a number of forces are acting like this, then how can we find out, say, if this is a F1, F2, F3, F4, F5, F6, F7, etc. How can we find out the resultant of all these forces, all these 7 forces? We can make use of the same one, that is parallelogram law, that is taking a pair of forces first and finding the resultant. Then find the resultant. Sometimes the resultant will be like this, and then this resultant, let be R1, and consider this resultant and the third force. Okay, then find the resultant and let be R2, then consider this one and the fourth one, etc., etc. In that way we can proceed, and finally we can get a single resultant. But it is a really cumbersome, tiresome and laborious process. Okay, so there is an easier method in which we will be utilizing the reverse of finding out the equilibrium, the resultant first, and then we will get into the resultant of all the forces. So in this process we will be finding the components of the forces in two or along two reference axes, two fixed reference axes. Okay, so suppose there is a force acting in this direction F. Okay, at an angle of theta degree with the horizontal. Okay, clear? So a force F is acting at an angle of theta degree with the horizontal. F is the magnitude, theta is the direction. Therefore, this force can be split into, this can be represented as two components like this. Okay, say if you are considering x and y axis as the reference axis, then a horizontal component and a vertical component, so this is the horizontal component FH and this is the vertical component FV. Okay, so in this way we can replace this force into, or we can split this force into its components along two reference axes. Okay, as this force is in a plane, so this force will have two components, one horizontal and one vertical. Clear? Or in other words, you can say, if we construct the parallelogram here, F will be the resultant of the diagonal. In this way, we are splitting up the force into two components along two reference axes. And the horizontal component is called as FH and the vertical component is called as FV. Now, what is the value of FH and FV with respect to F and theta? Okay. So, here you can see, if you drop a perpendicular onto this horizontal line, say if this is O and this is A and this is B, in triangle OBA, this angle B is 90 degree, therefore AB divided by OA will give you, what will be that? Sin theta. Okay. Similarly, OB divided by OA will give you cos theta. Clear? Sin theta and cos theta. AB by OA, OB by OA. Then what is OA? OA is F. So that will give you AB divided by F equal to sin theta and OB by F equal to cos theta. Okay. So from these equations, we can find out AB equal to F sin theta and OB equal to F cos theta. So what is AB and OB? AB and OB are the components of the force F along horizontal and vertical directions. So FH is equal to F cos theta and FV equal to F sin theta. Okay, FH is equal to F cos theta and FV is equal to F sin theta. In this way, we can split the force into its components, and this process is called as resolving the force into its components, or resolution of forces into its components. So if we are considering a force in 3D, then there will be one more component in the Z direction. Z direction which is perpendicular to this plane, or perpendicular to FH and FV. Okay, if you say if the force, the reference axes are X, Y and Z, then we can write this FP, FH, etc. in terms of X, Y, Z, that is Fx, Fy and Fz. In this way also we can write Fx, Fy and Fz. Okay, so here what I'm going to follow this method, that is Fp and Fh, vertical and horizontal components of the forces. Okay, so this is the basic. So we will be finding, we'll be applying this concept in the resolution of forces, and thereby finding out the resultant of a number of forces, that is more than two forces. If there are only two forces acting at a body, two concurrent forces are acting at a body simultaneously, then there will be we can make use of the parallelogram law of vectors. But if there are a number of forces, that is more than two forces are acting on a body, then we cannot make use of, or we cannot employ the parallelogram law of vectors, which will be a cumbersome process, and we can make use of this method. We will split the forces into its components, into fixed reference axis components, and then we will find out the resultant. I will show you how to. Then just wait and see. Okay. So before continuing into the problems, let us see what we can do using our so let us draw two reference axes, and this is the origin, this is x, this is y. Okay, so suppose forces are acting in each quadrant towards the origin. Towards the origin. Like this. Okay, let this be F1, this be F2, F3, and F4. Let this be F4. Okay, so if these are the forces acting simultaneously on this point. Okay, so this is origin, the forces are acting towards the origin in each quadrant, F1, F2, F3, and F4. Four forces are there. Now the forces can be, how to find out the resultant of these forces? We cannot make use of the parallelogram law of vectors. Okay, we cannot make use of it because there are four forces. So we will employ the resolution of forces here to find out the resultant. So what we are going to do is, we will split the force, each force into its corresponding components. We will split these forces into its corresponding components. Okay, so for F1, we will be splitting the force into two components along the horizontal and the vertical axis. So here for F1, the horizontal component will be like this. Okay, and the vertical component will be like this. Okay, here the angle will be let it be theta 1, that is angle of this force with the horizontal, or we can put the angle here also, no problem. Here also you can put the angle as theta 1. So this is theta 1, this is also theta 1. Therefore this component will be, what will be that component? What will be this component? The horizontal component will be F1 cos theta 1. F1 cos theta 1. Is it clear? Yeah. So it is F1 cos theta 1, and this is F1 sin theta 1. F1 sin theta 1. The vertical component is F1 sin theta 1. Okay. Now, as these forces are vectors, it should have the direction also. This force is acting in the or towards left, acting towards left. Okay, this force component, that is F1 cos theta 1 it is a magnitude. This force is acting in the leftward direction. Okay, so generally we make use of a sign convention, that is, if a force is acting towards right, it is taken as positive. Okay, if a force is acting towards left, then it is taken as negative. And if a force is acting in the upward direction, it is taken as positive. And if a force is acting in the downward direction, it is taken as negative. Okay, so this is the general sign convention used in many of the textbooks also. So we are also going to follow the same sign convention, that is, from or towards right, the quantities are taken as positive. Towards left, it is taken as negative. Upward, it is positive, downward it is negative. So here we can put the direction or sign. Say for this quantity f1 cos theta 1, it will be negative. Okay, if you are putting the arrow here in this direction, you need not put this minus sign. But when you are using this value in an equation, you must have to put this sign. Okay, so what about this one? This one also will be negative according to our sign convention. So minus f1 sin theta is the vertical component, minus f1 cos theta is the horizontal component of the force f1, which is acting at an angle of theta 1 with the horizontal. So similarly, we can split this force, the other force also. Say F2 is here, F2 is its horizontal component is in this direction. It is F2 cos theta 2. So this is theta 2, or this is theta 2. Okay, and this is the vertical component, that is F2 sin theta 2. What about the sign? Sign of this one? It is plus. Why? It is towards right. F cos theta 2 is towards right, and F sin theta 2 is negative because it is in the downward direction. Here is the sign convention. And for F3, the components are, this is F3 cos theta 3 because this is theta 3, and this is the vertical component F3 sin theta 3. Okay, what about the sign? Both are positive. It is vertically upwards. This is towards right. For F4, the horizontal component will be this one, and it is F4 cos theta 4, and this is the vertical component F4 sin theta 4. Okay, and regarding the sign, this is positive. This will be negative. Why? It is from right to left or towards left. Okay, so this is these are the components of these forces. Components of these forces. Forces F1, F2, F3, and F4, which are acting respectively in the first, second, third, and fourth quadrants. And also they are concurrent forces acting towards the origin. Okay, so in the first quadrant, both the components are negative. Second quadrant, the horizontal component is positive, vertical component is negative. Third quadrant, both of them are positive, and in the fourth quadrant, vertical component is positive and horizontal component is negative. You can see from the figure. Okay, so this is how we split the forces into its components. Split the forces into its components. Okay, then let us see another case in which the forces are acting away from the origin. Forces are acting away from the origin. So let us see that case also, then we will see how we can find out the resultant. All the forces on the quadrants are acting away from the origin. So let this be F1, this is F2, this is F3, and this is F4. So the components will be for F1, the components will be, this will be the vertical and horizontal component. This is the horizontal component. So F1 cos theta 1, where this is theta 1. Okay, and this is F2 sin theta 1. What about the sign? This is positive. This is also positive because this is in the upward direction and this is towards right, from left to right. It is F1 cos theta 1. And F2 will have these components. This is the horizontal component and this is the vertical component. So this is F2 cos theta 2 and this is F2 sin theta 2. F2 cos theta 2 and F2 sin theta 2, where this angle is theta 2. Okay, this is the angle theta 2, which is with respect to the horizontal. F2's angle with respect to the horizontal is theta 2. Therefore, this is F2 cos theta 2. And okay, so these forces, okay, let us continue. Component of these forces in these vertical and horizontal directions are minus F2 cos theta 2 and plus F2 sin theta 2. Minus is for the horizontal component, the minus sign is because the component is in the leftward direction, towards left, and this is positive because it is in the upward direction. Similarly, we can draw the components of other forces also. That is, F3 will have a horizontal component in this direction and a vertical component in this direction. If theta 3 is the angle with the horizontal, then this is minus F3 cos theta 3 and minus F3 sin theta 3, and this will be F4 cos theta 4 and F4 sin theta 4. Here the sign will be negative, here it will be positive. Okay, so these are the components of the forces F1, F2 and F3 and F4, which are acting away from the origin, and also they are concurrent forces. Okay, so the components are in the first quadrant, both of them are positive. The components are F1 cos theta 1 along the horizontal direction, F2 sin theta 1 along the vertical direction. For the second force, that is F2, the horizontal component is minus F2 cos theta 2 and this is plus F2 sin theta 2. For the components in the third quadrant, it is minus F3 cos theta 3 and minus F3 sin theta 3. And here it is plus F4 cos theta 4 and minus F4 sin theta 4. You can just compare these two figures, which is the forces are acting here in towards the origin. This is away from the origin, and the components you can just verify, just compare. Here both the components are positive, but here both the components are negative. Here both the components are negative, but here both the components are positive. Okay, so this is how we find the result, the resolved components of the forces in different directions, and also when it is acting towards or away from a point. Okay, now using this concept, we can find the resultant of the forces. Okay. I am erasing this part because this is not here. We already know the directions and everything, and the sign conventions also we know. So let us consider this case, that is all the forces are acting towards the center or towards the origin, towards the point under consideration. So what we have to do is we have to find the algebraic sum of all the forces. Okay, so in this case, what we have to do is we have to find the algebraic sum of all the horizontal components first, then find the algebraic sum of all the vertical components. So the algebraic sum of the horizontal components is denoted by sigma. Okay, sigma FH. Okay, so this is equal to what is sigma h? Sigma h is the algebraic sum of all the forces. Sigma fh is the algebraic sum of horizontal components. Okay, so here in this case, the horizontal component, or the algebraic sum of the horizontal components. I hope you know what is algebraic sum means. You have to consider the sign also, sign of the quantities also. So here in this case, the algebraic sum of the horizontal forces. Let us start with the first force. Its horizontal component is minus F1 cos theta 1, minus F1 cos theta 1, minus F1 cos theta 1. For the second one, plus F2 cos theta 2. Again here it is plus F3 cos theta 3, and here it is minus F4 cos theta 4. So this is the equation for sigma Fh, or the algebraic sum of all the horizontal components of the forces. Okay, or algebraic sum of the horizontal components of all the forces, that is sigma Fh. Similarly, we can find out sigma Fv also. What will be sigma Fv? Algebraic sum of all the vertical component of the forces. Okay, vertical component of the forces. Here we will start from the first one, that is minus F1 sin theta 1. Then for the second one, it is minus F2 sin theta 2. Okay. Then third one is plus F3 sin theta 3. Here also it is plus F4 sin theta 4. Okay. So these are the components of the forces in the vertical direction, and sigma Fv is the algebraic sum of all the vertical components. Okay. So we have sigma Fh and sigma Fv equal to, or they are expressed in this form. Okay. Now we have two components of two forces sigma h and sigma Fv. Okay, acting at this point. Instead of all these points or the forces acting, we can replace all these forces by the sigma Fh and sigma Fv. If we apply these two forces at this point at the origin, it will have the effect of all these forces. Okay, so we can draw a figure like this. Right here, a figure like this, and we can say this is sigma Fh and this is sigma Fv. Okay, because these are the horizontal components and these are the vertical components. Okay, and in the net effect of all these forces will be in the horizontal direction, and net effect of these forces will be in the vertical direction. Okay, so these are the assumed directions. When we substitute the values and find out the magnitude, it may be, or the sign, the net value, net force, it may be in the opposite direction. Okay, then we will have to put it in the opposite direction. Okay, yeah. So this is sigma Fv and this is sigma Fh. Okay, now we have two forces simultaneously acting at a point in these directions. Then we can make use of the parallelogram law. Here you have to construct the parallelogram. Here you construct the parallelogram. Okay, and the diagonal will be the resultant of sigma F and sigma Fh. Okay, actually all these forces are replaced by sigma F and sigma H, and if we replace these two by the resultant, then this will be the resultant of all of these forces. That is, we can show all these forces or replace all these forces by the resultant R. Okay, now how to find out R? R can be found out. The magnitude of R can be found out like this. R is equal to square root of sigma Fh square plus sigma Fv square. Okay, how can it be explained? That is, this is a right angle triangle, and square of this plus square of this side will be square of this one. Okay, if this is theta or alpha, then this side, the adjacent side square plus the opposite side square will be equal to square of hypotenuse in a right angle triangle. So R is equal to square root of sigma Fh square plus sigma Fv square. And to find out the angle alpha, we can use say tan alpha. Tan alpha is equal to opposite side by adjacent side. So alpha equal to tan inverse sigma Fv divided by sigma Fh. So alpha is equal to tan inverse sigma f by sigma fh. So using these two equations, we can finally find out the resultant. Okay. So this is how we can find out the resultant of a number of forces if there are more than two forces acting simultaneously at a point, and if the forces are concurrent forces also. Clear? So in this case, in the second case, when the forces are acting away from the forces, I will write just the algebraic sum sigma fh and sigma fp. Sigma fh is equal to, how it will be, we will start from the first one, f1 cos theta 1, f1 cos theta 1, it is plus, you can see it is plus, then minus f2 cos theta 2, here it is minus f3 cos theta 3 and minus f4 cos theta 4. Sorry, plus f4 cos theta 4. So two forces are negative and two forces are positive. So f1 cos theta 1 minus f2 cos theta 2 minus f3 cos theta 3 plus f4 cos theta 4, and sigma fv is equal to, here f2 sin sorry, this is f1, isn't it? This is f1. So f1 vertical components are sine components, f1 sin theta 1 plus f2 sin theta 2, then minus f3 sin theta 3, then minus f4 sin theta 4. So these are the equations for sigma fh and sigma fv. That is, in this case, the components will be different, the sign will be different. Okay, so we have found out this one. So in this case also, we have two forces, sigma fh and sigma fv, acting along horizontal and vertical direction, and it can have a resultant r at an angle of alpha, as we have found out in the previous case. That is, r is equal to sigma fh whole square plus sigma fv whole square and square root of, isn't it? Then alpha is equal to tan inverse of sigma fv by sigma fh. So this is how we find out the resultant of the forces acting simultaneously towards a point, and also if there are more than two forces acting simultaneously. Okay, so I think you have got a little bit idea of how to resolve the forces into its components and to find out the resultant of a number of forces acting simultaneously at a point. Okay, yeah, thank you.